In the last video we explored the send protocol and used Picoscope to decode the signal. However, we used the artificial signal coming from the Arduino Uno. This time we are going to use linear Hall sensor TLE4998C3 that uses a signal that is very similar to the send protocol. So this sensor is using something called short PWM code, which is a protocol that is based on the send. The sensor is digital and reports a 16-bit digital magnetic field and 8-bit digital temperature. Important thing for us is that the supply voltage is 5 volts and it's a 3-pin sensor, the one that we are going to use. So the connections are very simple. Pin number 1 is 5 volts, pin number 2 is a ground, and 3 is an out where we will get the send signal. Be very careful about this pin out, because it's very easy to use the sensor backwards. Look at these beveled edges, and do not rely on the markings on the sensor itself, because there are markings on both sides of the sensor. Technically speaking, the sensor allows for programming by a special protocol so that we can use some special features, but right out of the box it supports the synchronous operation. What it means is that to get the data out of the sensor, the microcontroller itself needs to send out a low signal called master trigger pulse, and only after that the sensor will wake up and then transmit the data in the send format. So in order to get the data out of the sensor, it's not enough to just connect an oscilloscope to the out pin. We also need to provide the master trigger pulse by using an Arduino Uno, for example. Let's see how this looks at the breadboard. So here is the sensor, and pin 1 and 2 are connected to the voltage and ground respectively. The out pin is connected to the oscilloscope, and also through a 200 ohm resistor it's connected to the input of Arduino Uno. Also through a diode and a 2.2 kilo ohm resistor in parallel, it's connected to the output pin of the Arduino Uno. The reason why this is done this way is that when this pin is high, then through the resistor it provides a pull-up for the sensor. When this pin goes low, then it pulls the line to ground by using this diode. So this is ideal for providing the master trigger pulse and thus wake up the sensor and get the data out of it. To test the magnetic field around the sensor, I'm using a magnet. This is coming from a popular magnetic switch for doors to see whether they are closed or open. So this is basically a magnet, and we can see that it attracts the needle of the magnetic compass, so I can always check how the magnetic field changes around the sensor. Okay, so let's see how the signal looks on the oscilloscope. So in Picoscope I have a trigger at 2 volts set for time base 100 microseconds per division, just like in the previous video. And what we see, the first pulse is a master trigger pulse coming from Arduino Uno, and we can see that because it's different from the rest of the pulses. The rest of the pulses are coming from the sensor itself after it receives and notices the master trigger pulse. the Picoscope has no problem interpreting this train of pulses, except that we can see that the checksum is not passed. Why is that? And the answer lies in the datasheet for the SPC protocol, which, while it's very similar to send protocol, there are some differences. And the difference is that the CRC calculation is done for all the nibbles, including the status symbol, nibble, and that's why it's a different calculation. However, the manufacturer is kind enough to provide the complete algorithm to do the CRC calculation, so it can be done fairly easily once you got the data, and this is exactly what I did in Arduino Uno. I'm reading this signal and then interpreting it by checking what the status is, what the data is, and you see here is that it's exactly the same nibble that is in the Picoscope. CRC is 0, and I compute what expected for this data, and it's also 0, so it's fine. Now we can proceed to checking what the data is. So we have 6 nibbles over here. What do they mean? And also there is a status. The status is 03. So let's go to the datasheet and check what we should get. Looking at the status, we see that the higher bits are 0, which means that it's a normal state for the sensor, and the lower bits are 3, which means it's 1-1 in binary. That means that the sensor is measuring the magnetic field in the range of plus minus 50 millitesla. Good to know. Now we need to look at the next 4 nibbles, and this will contain the magnetic field value. It's a 16-bit number going from 0 to 65,535 with the middle value, if I remember correctly, 32,768, corresponding to 0 magnetic field. If the value is lower than that middle value, it's a negative magnetic field, and if it's above that value, then it's a positive magnetic field. So all we need to do is to go and convert this number in hex 7964 into a decimal value and compare it to 32,768 and check what the field is. I do it automatically in Arduino Uno, and I'm getting minus 2.6 millitesla from that magnet that I'm using. Fun. If I reverse that magnet, then I'm getting around 2.6 millitesla, and so on. Now we also have 2 last nibbles to interpret, so let's take a look at the datasheet again. It's the temperature, and we have hex values 5 and 0, and we looking at this table, we notice that 5 is in binary 101 and 0 is 0, so that corresponds to 25 Celsius. Our temperature of the sensor is 25 Celsius. And of course, this is exactly what I programmed in the Arduino Uno. It reports 25 Celsius. So we are done here. We can take a look at the Picoscope and interpret the data. Unfortunately, we cannot confirm the CRC code. The checksum is not passed by Picoscope because the different algorithm is used. We are not able to get data out of this sensor just by an oscilloscope because we need a master trigger pulse from 8 to 9 microseconds, and that's where Arduino Uno comes in. And if we really want, we can use Arduino Uno to interpret this data as well, but it's not that easy. Because of this, time pulses are fairly short, just a few microseconds. We need to use special instructions in the Arduino Uno to notice and record correctly such short pulses. This is called input capture mode in the chip that's used in the Arduino Uno. And maybe that will be a subject of some other video. So see you in the future.